Hi, everyone. This is Nikola Cvetkovic, again, your host of CODEstantine Meetups and Conferences, the place where developers get together to learn, share experiences, and grow into better developers in the future. So as some of you know, CODEstantine has been started by a local nonprofit NGO from niche in Serbia called No Limit Hub. A few years ago as a conference, but then we decided to expand it and bring in people and experienced developers from all over the globe to share specific topics on certain topics that we do believe will be interesting to our audience. So we have been growing since ever since the start, and we keep getting new people joining CODEstantine community. So in order to make sure that you follow all the future events as well as watch all the past events, you can go and follow CODEstantine on different social media. Right now, we are in the middle of a series of online meetups. So more than 10 meetups already scheduled from people from all over the globe. 3 meetups have already passed. This is the 4th one. So make sure you go to the website and sign up for the upcoming as well. And you will also get access to all the previous talks as well. So follow CODEstantine and make sure you stick with us for all the cool content that's yet about to come. So my name is Nikola Cvetkovic. I'm the host of CODEstantine. I'm the founder of Product Hive, the product development agency specialized in building SaaS products, and Emito.io, a no-code business solution that helps you send multi-channel no-code business messaging through channels like SMS, Viber, Facebook Messenger, browser push, etc. And today we have 2 very special people, nonetheless, but from Google, the biggest player in the tech world, that has been evolving and introducing a bunch of new technologies over the years, and have been a role model to a lot of aspiring developers from all over the world. So with us today, we have 2 very special people. So Stephanie Wang, hi Stephanie, and Paulong Glynn. So I'll give a quick introduction about you 2 guys, and then you can go into the topic which is currently displayed on the screen. We'll explain also a little bit more what it actually is, although it sounds super complex. It kind of is, but can be simplified fairly well. So Stephanie Wang, currently in New York. She's a senior developer relations engineer at Google Cloud Platform. So Stephanie previously focused on building and maintaining BigQuery Java client libraries, which help developers interact with BigQuery APIs more easily. So basically, those who are interacting with Google API, you were one of the persons behind it that made it happen. And prior to Google, Stephanie worked as a software engineer in Morgan Stanley, led a people of 10 to build sales and trading applications. So interesting domain experience there as well. Besides work, as Stephanie likes to say, she's passionate about animals. She has a world-famous Instagram famous dog, and we'll share actually the hashtag in the chat. So for all of you, those who are animal lovers, go ahead and follow Sasha the Shiba Poo. Correct me if I said it wrong, Stephanie. But you also had, as you like to say, as you said it, opinionated semi-aquatic turtle, Bombshell the turtle. What's it called? So I'll share later on the hashtags of your best buddies, so people can follow as well. So welcome, Stephanie, and thank you for taking your time to be with us today. And also we have Paulong Glynn, senior developer advocate for Google Cloud. Hi, Paulong. He has a focus on in between the big data, data science, and machine learning. So these are all some buzzwords which we all been hearing a lot, and the two of you will actually kind of give us how it's used in the real world and what are some real world applications for this technology. And as far as I've read, Polong, you have taught data science to hundreds of thousands of learners online. So that's quite a lot of learners. I'd have to to acknowledge. So head down to that. So where did you get all these people to watch your stuff?
This is through some courses on Coursera.
So any advice there, how to get to that big of an audience? I'm sure that we also have some developers who might have some particular skill. So like one thing is to know something and one is to actually grow it to get to hundreds of thousands of learners. How did you do it shortly?
It wasn't just myself. It was a fantastic team. So kudos to them.
Awesome. Cool. So today we'll be speaking with Stephanie and Polong about the deep dive. We'll do a deep dive on time series forecasting and anomaly detection with BigQuery machine learning. So it sounds complex, but when you actually understand what this stands for, it's not that complex. So time series forecasting is a powerful way to use current and historical data to monitor, clarify, and predict cause and effect behaviors, which can better inform future decisions. So this is pretty much used in a lot of kind of, I'm aware of cybersecurity applications to kind of do real-time anomaly detection of, for example, critical incidents such as fraudulent behaviors or in a bad manner, but also can be used to kind of explore certain opportunities in business. So, for example, if you want to figure out a specific buying pattern of your customers, or like where the opportunities to upsell or grow, this can also be useful. And in this talk, we'll kind of take a look at the newest features in BigQuery machine learning. We'll see it in action and see how we can maybe simplify our workflow doing the time forecasting and anomaly detection. So without further ado, thanks again to all of you, to both of you for taking the time to be here. I will also invite everyone to leave comments and questions in the event on the side of our platform. You have the event tab, and just leave your comments there. I see some people have started to comment in stage. Let's try to keep it in one, just for the sake of not having to follow two discussions. So if that's okay, just use the event tab. As always, I will be jumping in from time to time just to maybe drill down on certain concepts that you guys mentioned and make sure that we're all on the same page and able to follow. So at the end, we'll have a short networking chat roulette, maybe some 15 minutes just to meet maybe 2 or 3 people who have been at the event. So you will see it on the networking menu on the left. Once the talk is over, we can all move there to meet a few people face to face, at least virtually for now. So thank you for all the attendees. Make sure you spread the word if you like the talk afterwards, and invite your colleagues who might still be at work to join in and leave the stuff that they're doing at the moment, since it's in some cases already past. In Central Europe, it's past 5 p.m. So time for some learning now. Stephanie, Polong, feel free to take the stage to hear more about BigQuery machine learning.
Great. Thank you so much, Nicola. Thanks for the warm introduction. It's absolutely our pleasure to be here today. So hello, everyone. Welcome again to our talk, a deep dive on time series forecasting and anomaly detection with BigQuery ML. So just to be clear, it's 100% okay if you're not familiar with Google BigQuery, because we will quickly go over the Google Cloud BigQuery product in our presentation later. It's also okay if you've never used BigQuery ML before or are not familiar, because we will delve into more details about BigQuery ML in our talk also. And we will take you through step by step, how do we do time series forecasting, non-time series forecasting, and anomaly detection on both sets of data very easily using BigQuery ML. So here is a quick summary of the content, and I just want to point out that some of these features we are talking about today have not even gone GA just yet. It's going to be coming out later this month. So you're really getting a very early preview of the latest and coolest that Google Cloud Platform is offering. So yeah, we're very excited to share. And a very quick intro in my own words, I work in Google Cloud as a developer relations engineer. I mostly focus on maintaining and developing the Java BigQuery client libraries. And you can find me on Twitter or check out my personal website. And I'm very lucky to be joined by my coworker, Paulong, over here. So Paulong, would you like to introduce yourself?
Sure, Paulong Lin, fellow, developer relations engineer like Stephanie. And our goal in Google Cloud is we sit under engineering. We work closely between the product teams who help create some incredible products on Google Cloud. And we also interact with a lot of developers or customers or people who are actually using the products. And we help kind of mediate the interactions so we can give product teams feedback. And we also can come to these conferences and give people the latest and the greatest of some of these products on Google Cloud.
Yep, that's exactly right. And before we go into a lot of technical details, I think we'll take a step back and take a look at some of the time series forecasting applications and just get ourselves warmed up to the concept. So over here, we have some practical business examples of how time series forecasting can help drive certain critical decisions. So in retail, I'm sure you're familiar, demand, sales, or inventory level forecasting could help business owners decide how much inventory to purchase and stock in order to avoid over or under allocation, which can translate into revenue losses. In workforce management or workforce planning, if we can forecast support tickets, calls, or store traffic, that can help businesses decide on store operation hours or the number of staff to hire so they can minimize their idle paid hours and maximize revenues again. In utilities industry, the ability to predict energy demand and commodities demand can help drive decisions on resource allocations. And in the travel industry over here, the ability to predict hotel occupancy, flight bookings is also very critical in making sure that customers' needs can be met and satisfied. The list goes on and on, right? So the point here is the ability to forecast accurately and promptly will soon become a necessity to stay competitive in any industry.
Now, if you imagine yourself as a retail industry data scientist or someone who's working to try to forecast the demand of several of your retail products, it can get really daunting very quickly as you approach lots and lots of retail products to forecast, especially when it comes to understanding, next week, how much should I stock? Or, the following month, how much of product X should I stock or, be concerned to kind of keep on the side so that we have enough of that particular product. So when it comes to forecasting millions of products, kind of procuring and managing the infrastructure to be able to handle this workload can get intimidating and challenging very quickly. And in the next slide, we'll kind of show you BigQuery. So Google BigQuery is the data warehouse on Google Cloud. So this is where you can store data, you can analyze your data, and you can also run machine learning on your data, all within BigQuery, the data warehouse on Google Cloud. So here's a quick example where this is a non-trivial select statement There's a couple of where clauses and a group by as well, and some regular expression as well here. And you can see in just 5.6 seconds, it's analyzing 500 or over 500 gigabytes of data. So BigQuery can automatically scale up, and as a user, all you have to do is simply run your query, and it will figure out how much does it need to use in the back end to be able to analyze your data for you. So it makes it really easy for a data analyst, a data scientist, to get to their insight as quickly as possible, all within the context of the data warehouse. Now, that is BigQuery, but what about machine learning? So this is where BigQuery ML comes into play. And BigQuery ML is essentially the machine learning capabilities within BigQuery. So by just writing the same sort of standard SQL that you would for your analytical workloads, like select star or group bys or where clauses or anything that you're doing in SQL, you can now, just by kind of writing custom machine learning code in SQL, you can now train and deploy machine learning models directly where your data sits in BigQuery. So I kind of talk a little bit about some of the models that are currently supported in BigQuery ML. So here, there's a whole kind of list of models that you can run and use in BigQuery. So for example, there's classification, there's regression, there are other model types like k-means clustering, there's time series forecasting, which we'll dive in a bit further today, recommendation engines, importing TensorFlow models from external places and bring them into your data on BigQuery. Or you can even export some of your BigQuery ML models to somewhere else so that you can use your BigQuery ML models outside of BigQuery itself. So that is BigQuery ML. And so now we're going to talk a little bit more about time series forecasting in the context of retail. So Stephanie, do you want to talk a little bit more about this?
Yeah, absolutely, Paulong. Thank you very much for the summary over there on the product. So one of the most popular use cases of time series forecasting, right, like we mentioned earlier, is demand forecasting. So for retail businesses, for example, there is a Goldilocks problem when it comes to inventory. You do not want to stock too little inventory because that could mean a loss of potential revenue. But you also don't want to stock too much inventory because that could be costly as well, because you will be wasting your very precious storage space with these goods that have limited lifespan, right? So what we're going to take a look at today is whether and how we can forecast liquor demand with BigQuery ML. So we're going to go through an example step by step, and you can see also how simple this sample can be applied to some of the other use cases you may have, maybe in your business or in your decision making. So before we jump into modeling or anything like that, maybe we should first take a look at our data at hand. So here we're using the BigQuery public dataset on liquor sales in Iowa, located in the United States. So we can see over here that the dataset contains transactional information on when liquor product like whiskey, rum, rye, and other kinds of liquor are sold in the state of Iowa in the US, and how many bottles were sold in a particular transaction. So that what we can do here is to forecast the total demand for each type of liquor over time across all the stores, right? And by the way, this data, you can access it very easily. You can just look it up and you'll be able to find it. So this is how the raw data, the training data is going to look like when we run the select statement below over here. So we have a date column, an item name column indicating what type of liquor it is, and a total amount sold column indicating the historical demand. So notice that there are some missing dates between January 7th and January 11th. So this is fine because the values will actually be filled in by BigQuery ML using local linear interpolation. So not to worry anything about here. So what happens with this one create or replace model query or statement is that as you run it, BigQuery ML will actually be creating up to 42 models for each of the individual items time series. So this ID column that's highlighted over here allows you to train multiple time series models in a single query, one for every item name in the data. So we don't have to write a separate query to train a separate model for each of these products. And among those potentially 42 models, BigQuery ML will then choose the best one for each item automatically using the auto-arrangement algorithm. So with, say, 1 million products that you have, that's up to 42 million models being created and tested behind the scene by BigQuery ML. And then returning to you only the best models, one for each of your 1 million products. And that's all within this one single query that I'm showing you. Another cool thing is this holiday region field allows us to even account for holiday effects when doing time series modeling with BigQuery ML. So by default, holiday effects modeling is disabled. So if you do not specify it, because it wouldn't know what holidays to take into account for. But we can specify it if we have at least 1 year of daily data. Because with this holiday effect being enabled, spikes and dips that appear during the holidays will be considered in our forecasting as well. So this is what we will see in the BigQuery console, Cloud Console, when we run the query. So again, these 5 models are the best models that BigQuery ML chose using the auto-arrangement algorithm from up to 42 models for each time series. The non-seasonal P, non-seasonal D, and non-seasonal Q, as well as the hash drift columns, define this time series model. The log likelihood, AIC, variance columns are relevant to the model fitting process. So it looks like over here that it's determined the demand for each type of liquor has a weekly seasonality, which means customers exhibit spikes in purchases on a weekly basis. This makes sense because people most likely drink more and party more on the weekends, and they tend to buy more alcohol, and leading to our weekly seasonality of the model.
Can I quickly jump in?
Yeah, of course.
Because not all of our listeners are on the same level of kind of understanding the background story. So like, I'd just like to drill down a little bit more. What's the actual data? Okay, this is the structure, but you're basically having like all the historical data of transaction that happened from date X in the past to date Y in the past, right? And the purchases that have been made, right? And then this model basically takes all this data, however, how much gigabytes of it, and it predicts the future consumption, future transactions that are going to happen based on the ones that happen in this data set that you take as the kind of the input, correct?
Correct. Yes.
Yeah. So basically, on this algorithm that you're mentioning, it's kind of running for you 42 different versions and scenarios, and it's basically playing it out till to the future. And how does it know which one of these 42 is the best? How to select the best ones since that part still didn't happen? So, like, what's the evaluation? Can you speak just a little bit more about the algorithm and how it determines what's
Sure.
your best?
We can talk a little bit more about exactly what happens behind the scenes for BigQuery ML. But of the 42 candidate models, what's used to select which one is the best is based off of what you see is the AIC score, the Akaike criterion. Mm-hmm. So of the 42 models, it calculates the AIC score. The lowest score becomes that kind of best model that BigQuery ML then kind of gives back to you. Mm-hmm. And the AIC score is a way to kind of calculate how well is the model performing, but also keeping it simple enough, because we want to kind of penalize the models if they become overly complex. Mm-hmm. So if it becomes overly complex, then maybe the AIC score will increase. Mm-hmm. So there's a bit of a balance between the two, and that's why it's this one metric that seems to be, a fairly decent metric to be able to quantify whether certain ARIMA-based models are better than others. Now, just to point out here, while the basis of BigQuery ML time series forecasting is based off of ARIMA, which is a very popular technique for time series forecasting, there's a lot of extra things happening behind the scenes. So we'll kind of dive into that as we kind of reveal what's kind of happening there.
Yeah, great. So awesome. Now we have the model being trained using the auto-ARIMA algorithm. Again, perhaps if you're interested in learning more about how that is done, reading up on ARIMA could also help over here. We're ready to use it to make a demand forecast for some of the future dates. So this is how our tabular data looks like once the forecast is made. Although this is only showing Black Velvet for 5 days, the full forecast results are going to be there for each type of liquor for however many units of days that you specify. So if you wanted to forecast for 30 days, you will have it for 30 days, and also for rye and rum and the other products as well. So to make a forecast, we simply have to run this SQL statement with an ml.forecast function. And we pass in 2 very important values. So one is horizon, and the other one is confidence level. So the horizon is the number of time points to predict in the future. And so this could be 30, indicating 30 days if you specify the unit of time is day, and up to a maximum of 1,000 data points, which I think is still a lot of days, because after a certain point in time, you may not want to actually forecast beyond 1,000 days, right? And then another very critical parameter over here is the confidence level. And this is a percentage of the future values that actually will fall into the prediction interval. So this is something that's a little bit more complicated, and I will delve more into confidence level in a little bit of time. But the next question you may have immediately is, how do we know if this forecast is actually accurate, right? So what we could do is we can compare the forecasted values to the actual values, because this all happened in the past, right? So to visualize this better, we plotted the forecasted values in orange and then the actual values in green on this graph, and indicated, and we also included our historical data over here to see how well BigQuery ML forecast function actually performed. And as we can see over here, for the most part, the actual values fell within the 90% confidence level, right? So just to make confidence level a little easier to understand, here are 3 different forecasts at 3 different confidence levels for the same model. The first one is 0.8, the second one is 0.9, and the last one is 0.99. So at 0.8, your confidence intervals are tighter or closer to the forecasted values. So the buffer is narrower. And at 0.99 confidence interval at the bottom, they are much looser. So you can be really confident that whatever the actual value will be, it will most likely fall within your specified confidence level. And also note that no matter what confidence level you decide to choose, confidence interval you decide to choose, the forecasted values will remain the same for the same model. So how would you actually make a decision on your confidence level? You may confidence interval, you may be wondering. And this is entirely up to you and your business use case. Do you want to be very, very certain that the actual demand will fall within your predicted range, right? So if that's the case, then you probably want to opt for 0.99, which is a higher confidence interval. Or do you want to have slightly narrower predicted range to help you better optimize your products or resources? In which case 0.8 might be a more appropriate confidence interval for you. So now at this point, you may be wondering, this is all so simple, right? So what is actually happening under the hood? And I think this also goes back to Nicola's question earlier, right? What is actually happening under the hood for BigQuery ML? So Paulin will go into great details on that.
Sure. So first of all, I think Stephanie already mentioned that if you have lots of data on lots and lots of different kinds of products, maybe they have different SKUs, SKUs as in different product IDs, and you have that across one store or multiple stores, within a single query to create your model in BigQuery ML, you can forecast up to 500,000 items in a single query So that's really easy to use. You can also auto scale the infrastructure automatically for you. So as a user, you don't have to worry about, do I need to spin up a cluster? Do I need a certain amount of CPUs or GPUs, or can I do this locally on my computer? Everything is scaled out for you automatically. So all you have to focus on is making sure your data is in the right shape and format, make sure your data is there, and just running the queries in order to get your predictions. So it's really simplifying a lot of the typically kind of time-consuming tasks and making it easier. So you can go from your data collection phase to your insights, your forecasted results in as short a time almost as possible. There's some other things that are happening that we haven't really talked as much about, but dealing with outliers in the data. Stephanie mentioned holiday effects. So depending on whether you're in the US or in Europe or by country, and if there's missing data, that will be imputed for you automatically as well. There's also something that's really, really, what I think is really cool. It's called adjusting for step changes, which I'll show you in a second. It also models with auto REMA, which we've covered already. And you can also orchestrate your BigQuery ML models using other services. For example, with Apache Airflow, or the managed version on Google Cloud called Cloud Composer. You can also visualize your results using something like Data Studio or your favorite visualization tool, whichever one you want to use. Essentially, your forecasted results will be in a table in BigQuery. So it makes it really easy for you to simply query that table to get your results and visualize it in something, even something like Looker, which could be really useful for both orchestration and visualization. So in the next slide, I won't go into this kind of complex flowchart, but this is kind of how BigQuery ML operates behind the scenes for you. And it does all these different steps automatically. So if you think like, what's so interesting about BigQuery ML? Well, you can actually do probably most of these functions or capabilities yourselves. If you wanted to do this from the ground up, you certainly could, and you perhaps could do it very well as well. But what BigQuery ML does is it simplifies this entire process for you. So Stephanie showed you 2-3 slides of SQL code that in each query didn't have more than maybe 15 lines of code in SQL. And really with those 2-3 queries, you can train up to 500,000 items to forecast. You can evaluate your models. You can make predictions. And we'll kind of talk about later, you can also detect anomalies as well in your data. So it really kind of simplifies that experience as a data scientist or as a data analyst, makes it really easy for you to kind of drive business value rather than focusing on how do I maintain this infrastructure? How do I write and maintain all my code to be able to do what I need to do? So that's kind of, in my opinion, the beauty of BigQuery ML. Now, I mentioned step changes here, so I'll kind of quickly go over what this means. So in the next slide, you can kind of see here, imagine you're looking at the popularity of something before the pandemic started to kind of occur. And then you're looking at the popularity of something after the initial wave of kind of the popularity spike in the pandemic. And this particular thing is looking at the daily Wikipedia page views for any titles containing the word sanitizer. So imagine hand sanitizer, or I don't know, alcohol-based sanitizer, or something similar. You can see everyone was really interested in, how useful sanitizers might be, maybe against COVID or something like that. But what's
we'll default back to not washing hands in a while. It seems like that. The trend is going there.
Well, there certainly is a trend, and we can talk about correlation in a separate case. But you can see here that the popularity was at a baseline low on the left-hand side. When the slide on the left-hand side, the baseline was very low. There wasn't that much interest, perhaps relatively speaking. Then there's a huge spike. And then after the pandemic, there's still a sustained increase in interest in sanitizer-related pages. So how does forecasting work when you have this kind of tremendous spike and then an increased sustained change? So here, what I've done is I've created a model that is simply trained on everything before the pandemic. So as you can see here, it's very hard to see, but if maybe in the next slide, you can see a zoomed-in view. Oh, sorry, if you could go back one slide, actually. This slide, exactly. So you can see here in a zoomed-in view, it's completely unable to forecast what's going to happen during the pandemic, right? There's no time series forecasting model that will probably be able to predict what happened during the pandemic. So that's a given. So of course, this is not going to predict anything very well, and that's perfectly fine. Now, in the next slide, you can see what I tried to do is I then tried to train the model with kind of a simple kind of ARIMA-based kind of technique at the end of kind of, after the spike had hit. So 2021, January, I trained the model up until the data for that day, and then try to forecast beyond what would happen. Now, if you don't do something called adjusting for step changes with your time series model, your model is going to get really confused. First, it sees, your sanitizer popularity at a baseline low, then there's a huge spike, and then now there's a sustained increase in popularity. How is it going to try to, rationalize, how to forecast in the future unless you adjust for step changes? So by default, time series modeling in BigQuery ML will automatically adjust for the step changes. You can see there in red, it's kind of highlighting the baseline before the pandemic, how it suddenly spikes. So it's kind of inspecting the step changes as it occurs. And then finally, the sustained level in red at the end of the kind of chart is still higher than where it was before. So it's accommodating for that. So when we actually, in the next slide, zoom into the forecast of this new model, it's able to appropriately forecast what's needed to be forecast despite all these changes that occurred in your data. So if you're a business that was affected by the coronavirus kind of pandemic, and you have all these fluctuations that are occurring, suddenly maybe something was low and now it's higher, or something was higher before, but now interest is lower and it's sustained lower, or vice versa, BigQuery ML will be able to accommodate for that and adjust for these step changes. So I think that's brilliant. And you could, of course, again, do this all yourself, maybe writing custom code, or you could do it by default, and it's enabled to make things so much faster, in my opinion, with BigQuery ML. Okay, Stephanie?
Excellent. Yeah, so that's really cool. We just saw how time series forecasting works with BigQuery ML, even taking into account things like step changes, right? Holiday effects, all these things. Another thing that you might want to do is anomaly detection with this time series data. So imagine if you had a series of time series data, and you want to know, like, is this an anomaly in the past, or will this be happening in the future as anomaly? So that's when anomaly detection can be very interesting and very helpful, because anomaly detection is really all about finding patterns of interest, right? So be it outliers, exceptions, or any sort of peculiarities in your data set, right? Anything that really deviates from expected behavior within your data set. So the ultimate goal of anomaly detection over here is not just an algorithm or a working model. Instead, it's really about finding the value or insights that anomalies can provide. So for banking and insurance companies, it could be the number of customers protected from fraudulent transactions or insider trading detection. For a technology company, it could be money saved from preventing software intrusions. For a business, right, it could be money made from anticipating sudden demand changes. And in medicine, it could mean earlier detection of certain diseases or easier treatment. The list goes on. So this is why it is really critical to be able to respond quickly to anomalies. And if your data is already in BigQuery, that becomes even more easily accomplishable. So now we can take a look at how this can be done with BigQuery ML.
I mute myself. Okay, great. So when it comes to anomaly detection in time series data, you may have anomalies historically, as in data that has, or things that have occurred in the past, and you want to look back and observe, have there been really unusual things that have happened? So for example, here, there's a major spike there in the past, so maybe you want to detect that automatically without having to declare a rule or a threshold, right? You don't want to say like, oh, I want to find anything in the past that was above this level of 400 or something like that. You want to automatically detect anomalies through a more of a statistical approach. But without having to dive into statistics too much, you can actually do this directly with BigQuery ML. Now, before we go on to that, I want to first talk about the next slide, which is the other side of the coin, which is trying to predict, trying to detect anomalies on new data, so new incoming data. So let's say you have your model trained up to a certain point. So as new data comes in, as maybe new transactions are coming in, are those transactions or is the popularity of sanitizer for that particular day, is that an anomaly? Is that kind of unusual? So as new things come in, you may want to have that model ready to go, trying to detect whether or not something's anomalous. So you have sort of historical looking anomalies, and you also have these kind of forward looking or anomalies that you're trying to detect. And BigQuery ML will work with both. And so in the next slide or two, so we have anomaly in training data, anomaly in new data. And here in the next slide, Stephanie can kind of go through the code for anomaly detection for training data versus for new data. And it's really simple.
Yeah. So to do it with BigQuery ML, again, no surprise, all you have to do is to run an SQL query, right? So over here, we're using the ml.detectAnomalies function over here, and we're passing in anomaly probability threshold, and one is done for historical data, and then the other one is done for forward-looking anomaly detection for the future data, right? So as simple as that, you just have to specify a particular anomaly probability threshold, which indicates to the algorithm, like, what do you consider an anomaly? What is your tolerance for an anomaly? And then BigQuery ML will handle it for you and then produce the anomalies for you in your data. So this is what we have when we put the anomaly probability threshold as 0.95, and you will get a column that tells you whether the role is considered an anomaly or not. Yeah. Awesome.
That's great.
So yeah, and feel free to ask us any questions, if you had any. I know we're going over a lot of materials very quickly, so don't feel, deterred from asking us any questions. Awesome. So that pretty much wraps up our time series data topics on time series forecasting and anomaly detection. So now we may be wondering what happens with anomaly detection with non-time series data, because obviously not all the data sets are going to be time series data, right? How do you accomplish anomaly detection with non-time series data? So when it comes to anomaly detection, right, one of the key challenges really is it can be very difficult to know how to define what an anomaly is. Right? How do you actually define and anticipate unusual behavior, right, that just happens maybe all of a sudden or maybe not, right, like a network breakdown, internet breakdown, anything like that. So if you have label data with no anomalies, then yeah, you can choose from a variety of supervised model types. But what can you do if you do not know what kind of anomalies to expect and you do not have label data, right? So this is when we have to turn to unsupervised models and methods. And that can be done with BigQuery ML for both time series data and non-time series data. And I just want to point out over here that the supervised anomaly detection is already GA'd with the product, and you can try it out already. The unsupervised anomaly detection is actually coming out very soon, hopefully by the end of this month. So wanted to just put it out there that these are very, very new features. And with the unsupervised models, I would like to start with autoencoders. So let's take a look at how autoencoder models work.
So just to jump in and maybe clarify on one thing. So first we were talking about forecasting, meaning predicting data in the future. So like when we ran the first line of code, it kind of gives us the estimates what the model thinks will be the sales in the future. The anomaly detection is a different thing, how I understand it at least, is to actually you train a model, but then it doesn't predict your future data, but it serves as a kind of checker for the new data that's coming in and kind of flags if something is an anomaly in real time. Is that correct, or or am I misunderstanding something? That difference was not clear.
So, okay, so I was just going to point out, yes, anomaly detection is trained using your existing training data, but you can detect anomalies in your new data. So you can also use the same model to detect anomalies on your historical data. So it is two different things. So yeah, time series forecasting is about predicting future demand, future things happening, but anomaly detection is simply looking at your data. So for example, you have been using credit card, and then all of a sudden, maybe you charge an abnormal amount, and then you may be getting an alert from the bank saying, hey, this looks like some fraud or anomaly. So that is for new data, incoming data.
Yeah, cool. Just wanted to make that clear so that people don't get lost.
Yeah, definitely. Awesome. So let's go back and take a look at our autoencoder model and how that actually works.
Great, thanks, Stephanie. So I have a quick kind of exercise for everyone to try to attempt. It's a difficult kind of mini exercise, and even I can't do this. It's very, very difficult, but maybe some of you can, depending on your skills in chess. So this is the goal of this is try to explain what autoencoders are for those of you who are not familiar with autoencoders. Okay, so in the next slide, before Stephanie changes the slide, in the next slide you're going to see a chessboard. Okay, and it's going to have lots of pieces on it, and we're going to display it to you on the screen for just 5 seconds, and then after that we're going to replace it with a completely blank chessboard. Now your goal is within those 5 seconds, try the best as you can to memorize where every single chess piece is on the board. So there's maybe pawns, rooks, knights, bishops, king, queen, bishops. I think I said that twice, I can't remember. And then there's white pieces and there's dark pieces as well. So try to remember exactly where all the pieces are. And then at the end of the 5 seconds, try to quickly reimagine where they are on the chessboard. Okay, so Stephanie, 5 seconds, let's go.
5,000, 4,000, 3,000, 2,000, 1,000, that's it.
Okay, so for those of you who are able to, that's absolutely fantastic. Please reach out to us on Twitter. I'd love to kind of play chess with you. But for those of us who aren't able to, trying to recreate this chessboard is very, very difficult. But in the next slide, as you can see, there are grandmasters in chess who they're really, really good at chess, and they've played chess, tens of thousands of games, maybe hundreds of thousands, maybe millions of games. I don't know, but they're so good that within those 5 seconds, they were probably able to determine where each of the pieces are in relation to each other, so that after the 5 seconds, they could recreate it very quickly in their minds. So, Queen's Gambit moment. That's right. And in the next slide, sorry, before we go into the next slide, sorry, go back 1 second. Okay, so in the next slide, we're going to repeat the same exercise. Okay, in the next slide, we're going to go and show you another board for 5 seconds, and just for you to try to memorize again. All right, so go ahead, Stephanie.
5,000, 4,000, 3,000, 2,000, 1,000, 0.
Okay, so I probably should have included a blank kind of chessboard there, but this chessboard is actually different from the one that you saw before. The one that you saw before was actually a legitimate chessboard, but this chessboard is actually an illegal chessboard. By illegal, I don't mean that it's committed a crime. I mean that there are pieces on the chessboard that shouldn't be where they actually are on this board. You can see here, I've tried to point out some of the placements of certain pieces on the board that don't really make sense. It's like, how did this even come to this particular location on the chessboard? And there are even some pieces where, they just shouldn't be there. So if you are a chess grandmaster, so maybe if you self-identified that from before in the previous exercise, maybe you had a lot of difficulty in this particular exercise, in the second exercise with an illegal chessboard. So in the next slide, I'll kind of use this to kind of summarize. Oh, I think we skipped one. If you go back one more, sorry. Yes, that'd be great. So if you give a legal chess layout to a chess grandmaster, and if you ask them to recreate it visually or even put it back on a chessboard directly in front of you, and you count how many times they make an error, the chess grandmaster is likely to make 0 or probably very minimal errors. But if you have the same chess grandmaster and you show them these illegal chess layouts that completely make no sense whatsoever, that are these chess layouts that a chess grandmaster would never encounter in a normal kind of chess game, an illegal chess game, then they're more likely to recreate it with a lot of errors, because the rules that they've kind of developed in their minds no longer apply to this illegal chess layout. So the chess grandmaster here in this next slide, I've kind of made that analogy to an autoencoder, or the chess grandmaster is our autoencoder, whereby they've maybe created some mental rules like, both sides have castled towards h, or there's triple pawns protecting the king, or some other kind of ways to summarize what's happening on the chessboard, so that it's really easy for them to later recreate and reconstruct the chessboard. So we have our original input, which could be the chessboard, and then the reconstructed input, which is the chess grandmaster's attempt at trying to recreate the chessboard. So the chess grandmaster here is our autoencoder. It's trying to find these abstractions and then recreate what they had seen earlier. So imagine with like digits. So if, this is a very popular example with handwritten digits. Can you create an autoencoder to take in images of handwritten digits and train that autoencoder to be like that chess grandmaster? But instead of being a chess grandmaster, they're essentially a handwritten digit recognizing grandmaster of sorts. So in the next slide, we can see here that you can train an autoencoder to try to recreate all these handwritten digits in their minds, or well, essentially within the hidden layers of the autoencoder. So in the next slide, you can see if you ask the autoencoder to then try to quantify, if we try to quantify the mistakes that the autoencoder makes, maybe for certain numbers or certain digits that are very common kind of patterns of writing the digits, like the one is, that's one single stroke is very common, very, it's consistent across how everyone writes that one. But then maybe the 2 or maybe the 4 can be written in so many different ways that maybe has a bit more trouble trying to reconstruct it. So because they're more difficult to reconstruct, we could say that they are more anomalous. So they're more like anomalies. So the higher the error, the more likely the data point is an anomaly, because the autoencoder had trouble reconstructing it. So as long as we have some measure of error between the actual input and the reconstructed output, we could use autoencoders to find some sort of threshold. We could say like maybe any kind of input output that had an error above, let's say 25 or 20, we call everything above that to be anomalous. In this case, the 2 will be considered anomalous. Now, kind of depending on how you set your threshold and so on, that's always kind of up to you as a user or as a data scientist. But you can use that as a way to determine what are your anomalies in your data. Now, of course, when it comes to images and data warehouses, that doesn't really kind of translate very well. So when we think about BigQuery, data in BigQuery, we're thinking about in terms of structured data. So in the next slide, let me see. Right, so if we have a new input as well, so maybe the autoencoder is trained on everything on the left-hand side, and on the right-hand side with a 9, it's a completely new input. It's never seen this sort of 9 before. It may have seen other 9s, but not this particular handwritten digit of a 9. And when we try to reconstruct it, you can see it's having difficulty reconstructing it. And for whatever reason, it has that difficulty. Maybe it's because no one writes 9 with the diagonal kind of orientation like that. Most people write it maybe in a straight orientation. So they have trouble with this. So again, maybe this 9 is considered an anomaly. So that's kind of how it works. And I've kind of talked about the threshold here. So you can go on to the next slide. And so if we say, like maybe of the training data, maybe 20% of my data, I want to consider them to be anomalous. Maybe not 20%, maybe like 2% or 1% of my data is anomalous. We can set the contamination to be 0.2 or for 20%, so that the top 20% of descending mean squared errors, in this case, could be used as the cutoff threshold. So if we, in the next slide, I believe, if we sort all the digits by increasing mean squared error, and we take that 20% as anomalous, then anything above 22, a value of 22 for mean squared error in the historical data or in future data will be considered anomalous. So that's kind of how autoencoders conceptually work. Now, how does this actually work in BigQuery and BigQuery ML? I think Stephanie will happily explain this to you.
Yeah, thank you very much, Paul. That was a really interesting kind of example, right? That everyone can visualize how autoencoder works. But how do we actually apply those concepts in real life in BigQuery ML terms? So we'll take a look at a realistic business problem to solve here. Nicola, do you have a question? I was just wondering. Okay. Never mind. I thought you, Nicola, unmuted, so I thought there was a question. Okay, that's fine.
Can you hear me?
Yeah, I can hear you.
Is it my Wi-Fi? Okay, cool. Yeah, I just wanted to reference your chess moment. So I've been actually watching a few of the games of AlphaZero. So that's basically Google's AI engine for chess, which has beaten everybody that it played against, and like it's really phenomenal how it works, and like the decisions the engine takes and the moves he makes, and kind of even sacrifices which were never standard for a typical chess that typical grandmaster would never consider. So I think it's an interesting topic sometime for the future to just dive into AlphaZero and how it works, and like a little bit of theory behind it. But it's super interesting, and how it managed to learn all this and kind of act in a way it does right now.
Awesome. So yeah, let's go back to our example with an actual use case. How do we apply the autoencoder in theory in real life, right? So the business problem that we're going to investigate over here is how to identify fraudulent credit card transactions given some data. So over here, the data we're using are the popular credit card fraudulent detection dataset on Kaggle. So this, I think, also is available on BigQuery public datasets, and you can find it under the ML datasets if you're interested in taking a look. Right, so this data records credit card transactions made by European cardholders in 2013. And this dataset as a whole has about 500 frauds out of about 300,000 transactions in total. So that's about 0.17% in terms of fraudulent transactions out of the total number of transactions. And the technical challenge over here is how do we deal with this sort of imbalanced data sets, right? Because only 0.17% of the transactions in the data sets are being marked as fraud. And to look at it a little bit more closely, we have a time column, which is one of the features that contains the number of seconds between the first transaction in the dataset and the time of the selected transaction. And then we also have these features V1, V2, V3, all the way until V28. So if you, again, look at the actual public dataset, you will be able to see all these columns. So these are actually transformed into these anonymous columns or say features via the dimensionality reduction technique in PCA to anonymize this data, because we do not want to disclose any personal identifiable data over here. And then we also have a column amount, which is representing the transaction amounts over here. So that's pretty much how what we have as our training data, our raw data, right? So the question we want to solve over here, the problem we want to solve over here is which rows, given this table of data, represent anomalies. And the way we do it with BigQuery ML, again, first is to create a model with a very simple SQL statement, right? So how we do this is we're going to, again, run our create model statement, and we specify the various model options over here. So we're passing in our model type as autoencoder. That is the awesome model that we just looked at earlier that Paulon showed you. We're going to be using the same concept over here, and we're also passing in some of the other options. And we have a long list of supported model options that can be found on the BigQuery ML documentation page. And over here, specifically, we are putting in rectify linear as activation function, 8 as our batch size, 0.2 as our dropout. So we have hidden units that's changing from 32 to 16 to 4, and then back to 16, and then back to 32. So this one represents the number of hidden layers in the deep neural networks. And then we have a learn rate, and then linear regression activation, maximum iteration, and then finally for optimizer, we are using the Adam algorithm as our deep neural network optimizer. So everything can be done over here, again, all within a single query. And then over here, we're selecting everything but the time and the class. So class is actually a response variable, and it takes the value of 1 in case of a fraud and 0 when it is not a fraud. Right, so to detect anomalies in the training data, all we need to do is to utilize the ml.detectAnomalies function. We can use the same data used during training that we looked at earlier, and then we can detect anomalies in both historical and new data, like we mentioned before. So anomalies over here are identified based on each input data points reconstructed error, like what Paul mentioned earlier, the reconstruction data points, which so if it exceeded the threshold determined by this contamination value that the user inputs, then it is identified as an anomaly. So earlier, remember we were putting down 0.2 as our contamination, which means 20% of that is going to be considered anomalies. And over here, we're talking about like 0.1 is 10%. Top 10% of descending errors from the training data will be used as our cutoff threshold. Right. So this is what we get when we run this anomaly detection function, right? So we have a column that indicates whether this role is considered an anomaly, and then we have our favorite mean squared error, which is critical in determining whether the data point is considered anomaly or not. Right, so again, the ml.detectAnomalies function would first compute this mean squared error for each data point between its original value and the reconstructed value. So remember the original 1 and the reconstructed 1, the original 2 and the reconstructed 2. And then the contamination value, which is something that we can specify, will determine the threshold of whether the data point is considered an anomaly or not. So again, if we're putting down 0.1 as our contamination value, that means the top 10% of descending mean squared error from the training data will be used as the cutoff threshold. Awesome. So let's try to visualize this.
Before we visualize it, just one second. If you go back to the previous slide on the syntax for ml.detectAnomalies, a question that you may have is, why do you choose 0.1 or why not 0.2 or why not 0.01? So it really kind of depends on your use case. And as Stephanie mentioned, was it 0.17% of the training data was historically classified as anomalies. But if you imagine yourself to be, for example, a bank or an organization handling transactions, and you're trying to determine, in the future what percent will be, will be anomalous, then you don't maybe want to be caught in a scenario where a fraudulent transaction occurs, but you didn't flag it. So you let it pass by accident. So maybe it might be better to have a slightly higher contamination, right? A slightly higher buffer for this to happen, right? So in those particular situations, you may want to have a slightly higher contamination, or in other situations, maybe you want to have a lower contamination value. So that is entirely up to you. So I also note that there is a comment in the chat here by MS, and MS states that maybe the data first needs to be balanced to ensure that the techniques will work well for training. Well, that is certainly true for supervised learning. So if you have 99% of your data is a value of 0 and 1% is a value of 1 or something similar, then you may want to figure out how do you balance the data set a little bit more. So when you run your supervised learning classifier, whether it's logistic regression, XGBoost, DNN, whatever you choose, it'll have a better chance of predicting what you're trying to predict. But when it comes to unsupervised learning, especially for anomaly detection, you don't necessarily have to have that balanced data set, especially in some cases. So here for credit card fraud detection, maybe in this particular data set, we have the labels. But what if you didn't have any labels whatsoever? And your goal was, I'm trying to find anomalies. And that is a much more difficult problem where you cannot balance it because you have nothing to balance between. You don't know what to balance between, fraud versus not fraud because you don't have the information a priori. So in that particular situation, you're essentially just simply stating, 0.1 as my contamination, and then trying to further investigate the resulting anomalies that have been detected. So in the event that you do have some labels a priori, and you do run it through an unsupervised technique like autoencoders, now here is where we can show you some charts of what it may look like. So if you go to so this chart here, so here we're plotting the reconstruction error. So remember the MSE. So the x-axis is from left to right, increasing MSE. So you can see for the majority of the time when there's a lot of MSE, more closely to the right, you have a lot, it's more likely to be fraud. Whereas when the reconstruction error is closer to 0, it's more likely to be non-fraud. So in this particular scenario, if you imagine that you have a new transaction coming in and your autoencoder tries to reconstruct it and has that MSE of, let's say, 20, we say 20 or whatever value you want. That 20 value of MSE, anything above 20 value of MSE, we're going to send an alert to our customer and have them verify that this transaction is indeed what they were looking for. So we don't necessarily have to block that transaction right away. We could just simply notify them, ask them to verify it. And so that way we can still have a bit of a buffer, 0.1 contamination may still be okay. Or maybe, tweak it a little bit to 0.5 or 0.05 or something like that. So that's kind of how you may consider using anomaly detection with autoencoders in practice. So,
awesome. Thank you very much, Paulo. So another model that we really want to share today is the k-means clustering model. That's different from the autoencoder model.
Yes.
Paulo, go ahead and let's talk about k-means clustering.
Okay, so we're going to cover yet another different kind of algorithm here. So for those of you who are familiar with k-means clustering, the whole goal of k-means clustering is to using an unsupervised technique, automatically segment your data into data points that are very similar to each other. So if you want to find two groups in your data, you're looking for k is equal to 2 or 2 clusters in your data set. So let's kind of go through an example and kind of see what it looks like in the context of anomaly detection. So here we have some data, just 2-dimensional data in XY axis. Doesn't matter what it is. But let's say these are our data points. We have about 20, 30 data points here. So if we were to run k-means clustering on k is equal to 2, we're trying to look for 2 clusters, it should automatically find in the next slide or 2 when it turns green and blue, it should find, sorry, one more. There we go. So we have 2 clusters there. One kind of the green dots and one which is kind of like the blue dots that it automatically detects for you with k is equal to 2. Now, if we observe the kind of the nature of this data, right, we have our centroid, which is the center of our clusters. And we also have our kind of a cluster radius, which is kind of like how dispersed is this cluster. So we have, maybe the cluster 1 kind of looks like it has a very tight cluster, and cluster 2 has a much larger radius. It has a much more dispersed cluster because the variance between the distance between each data point to the cluster centroid is a little bit further out. So if we were to summarize our k-means model of k is equal to 2, we could summarize it based off of the cluster centroid as well as the radius. So now that we have our k-means clustering model, how do we then detect these anomalies? Now you saw from before that there were these 3 points, point A, point B, and point C, that seemed to be kind of odd. It kind of fell slightly outside of the radius or kind of seemed to be a little bit further away from everything else. So how do we quantify programmatically or automatically, how to quantify that these are indeed outliers? So, you may consider first using absolute distances. From what? From the nearest centroid. So for example, point A to its nearest centroid is cluster 1. So here we have that line there. And point B to its nearest centroid, by absolute distance, we can draw that simple line there. And then point C to the centroid of cluster 2, we have that line there. And so we have maybe, point A and point B have the similar distance to its nearest centroids of 4. And point C has a furthest kind of distance of a value of 10. But if you were to look at these, and in the next slide you can kind of point this out, point A still somehow seems a bit more anomalous than point B, because point B in relation to the size and the dispersion of cluster 2 seems to be less of an outlier compared to point A to cluster 1. So is there a way to better quantify this with respect to the size of the cluster? And there is, but just by simply using normalized distances. So here, suppose we kind of normalize all the radiuses to be 1. So now the distance for point C to its nearest centroid is going to be 2.2. So 2.2 is a distance, 2 times 2, the distance of the radius of the blue cluster is going to be the normalized distance for point C. Now for point B, sorry, just go back one slide, Stephanie. For point B, we're now going to calculate the distance to the blue centroid and the distance to the green centroid based off of each of their radiuses. So we find that point B to the blue centroid is just maybe 1.1 times the blue centroid's radius. Whereas for point B to the green point, it's a value of 15. Sorry, just go back one slide, Stephanie. Thanks. To 15. So we take the smallest of the two and we say, okay, point B is the closest to centroid, the blue centroid. So we just keep that value of 1.1. And then again, we do this for point A. So in the next slide, we do this for calculate for point A, where it is 3 times the distance towards the blue centroid, but only 6 times the radius towards the green centroid. And now we can sort this. So if we go to the next slide, we can sort this. We say, actually, based off of normalized distance, we find that point A has, in terms of the smallest distance to its nearest centroid, normalized distance-wise, point A is the furthest, followed by point B, followed by point C. So based off of this, sorry, I kind of mixed this up, point C and then followed by point B. So based off of this, point A is actually the most anomalous, whereas if you looked at it from an absolute distance perspective, point C was the most anomalous. So in this kind of consideration, normalized distance is probably the better method. And that's the method that's actually used when we run a k-means clustering model in BigQuery ML, and then we can use this same concept to detect anomalies. So in the next slide, here we have the, we can say like, so as I mentioned here, the centroid labels can be different with normalized distance versus using absolute distance. So in the next slide further below, here we can see that if we try to quantify anomalies, again, we can try to sort all of these distances from highest to lowest. And then by using, again, a contamination value, if once you sort it, can we take the top 10%, the top 20% of descending normalized distances, and then use that value of 1.6 or 1.4 or whatever we choose to do, to use based off of our contamination value as the threshold to further detect whether something is going to be an anomaly or not. So at the end of the day, in the next slide, you can see here, if we set, if I think that 20% of my training data is anomalous, then I'll set contamination to 0.2. So based off of the top 20% of descending, not MSE here, I made a mistake, but descending normalized distance, then the cutoff threshold would be anything greater than 1.6. We would consider that to be an anomaly.
Yep, that's awesome. So again, let's take a look at how the concept of k-means clustering that we just looked at earlier is applied in real life with BigQuery ML in practice. And again, we look at the same set of data, which is the fraud data, as an example. And the question remains, right, how do we determine which rows that we see over here are anomalies? Right. So with k-means clustering method, we also will start by creating a k-means clustering model using the SQL statement. So again, we run a create model, and then we put in our options. This time, we're putting in k-means as our model type, and we're specifying that we think that there are 8 clusters, but this is a number that you can specify for yourself. If you have some vague understanding of the data set, you can specify how many clusters you believe there could be, and then we can also add in some of the other k-means options, such as a k-means init method, etc. right? And then with this k-means clustering model trained, we can run the ml.detectAnomalies function to detect anomalies in the training data, or also again in the new input data in the future. Right, and here we're showing 0.1 as contamination, but in the real scenario, perhaps 0.001 would be a better contamination, given the fact that only 0.17% of this imbalanced data set are frauds, right? So yeah, so based on what Paulong just mentioned earlier, right, the anomalies using the k-means clustering model are identified based on the value of each input data point's normalized distance to its nearest cluster, right? So if it exceeds the threshold determined by the contamination value, which we specify, it is then identified as an anomaly. So you see how the explanation here is very similar to our autoencoder, but then also very different, right? So with a k-means clustering model and also data as our inputs, our ml.detectAnomalies function would first compute this the normalized distance. Actually, no, it will first compute the absolute distance for each input data point to all the cluster centroids in the model. And then what happens is it would normalize each distance by the respective cluster radius, which is kind of the same process which we went through earlier with our data point example. And also, so the cluster radius is defined as the standard deviation of the absolute distance of all the points in the cluster to the centroid, right? So for each data point, the ml.detectAnomalies function return the nearest centroid ID based on this normalized distance over here. So again, the contamination value, sorry. Oops. Sorry, I think, did I just go dark? Okay, yeah, sorry. Let me share.
The screen share.
Oh, my bad. I'm sorry. Okay, are we back? Okay. Yeah. I apologize for the interruption over here. So yeah, just wanted to quickly re-emphasize that the contamination value over here, which we looked at a little bit earlier, is the value that's specified by the user, and this again determines the threshold of whether a data point is considered an anomaly or not, right? So a contamination value of 0.1 means the top 10% of descending normalized distance in this case from the training data will be used as the cutoff threshold. Right? So if the normalized distance for a data point exceeds this particular threshold, then it is identified as an anomaly.
So how do we correct the system once we kind of figure out that some things which were not kind of seen by the model as anomalies, how do we correct it and kind of give it inputs so it improves over time?
How would you correct it for supervised machine learning techniques? I'm trying to think of the solution for both. For unsupervised techniques, I think you'd have to pass in known anomalies, almost your labels, and then kind of validate it from there. Maybe adjust your contamination value based off of your known values for anomalies. But at the same time, too, it can be difficult to determine whether something is truly an anomaly, depending on your use case. Mm-hmm. So it's a tricky problem. It could be with more data. It could be with labeling. It could be with using this as a precursor to yet another model, potentially. Maybe the result of ML.detectAnomalies on unsupervised techniques. The is anomalies true or false here? It can be used as a feature in a downstream supervised model as well. So yeah, this kind of ties into how do you connect models together and how do you orchestrate this together? And I think it actually happens to be that Stephanie will cover this a little bit in this next section as well.
Cool.
Yeah, exactly. So I think it's important for some of the users to start thinking about, scheduling and automating model retraining with some of the schedule queries. My apologies, my dog is making some noises. So sorry, let me just stop.
No worries.
So the reason is because she sees the turtle walking around and she's upset all of a sudden. She's like that sometimes. Most of the time she doesn't care all of a sudden. But anyway, yeah, so what we could do is try to tell BigQuery to, retrain these models from time to time so that you can get, better models over time, and then you have better accuracy over time as well. And fortunately, that is covered by BigQuery and BigQuery ML as well. It's very straightforward if we just simply go for scheduled queries, right? So if you're like many businesses that need to create fresh time series forecasts based on the most recent data, right? So you can use these schedule queries to automatically rerun your SQL queries. So that could include your create model statement, your ML.forecast queries. You can also do so for ML.detect anomalies queries. And you can set up how often you want to rerun these queries and whether you want to start them on a certain day and on a certain day, and even send out email notifications, right? So here we're showing an example of a schedule query to retrain my ARIMA Plus model every single week. This also is supported by pop-up messages. So if you want to do something downstream, after you train your model, you can do that quite easily as well. And this is how it looks like once your query is scheduled. But there are also other ways to do it. I believe Paulo mentioned briefly earlier about orchestration with Cloud Composer, which is a Google version of Apache Airflow. There are ways to do that as well, outside just the BigQuery schedule query method that allows you to have, other downstream events, emails, or Slack notification. So yeah, that's all easily accomplished. So now we have reached the end of our presentation for today. I really hope that everyone could have a few takeaways from it. If you have further questions or other concerns, whatever, please feel free to reach out to either me or Paulong after this event. We're very happy to talk with you. And also, you could find us on our YouTube recorded session if you missed some parts of this presentation. Yeah, and thank you again for having us today.
Thank you.
Awesome. Awesome. Thanks to both of you for taking the time to show up, prepare the presentation, and give this kind of fairly quick overview of a bunch of different features and kind of possibilities that you can do with BigQuery ML. To be honest, looks too easy to be true when you look at it. Just pass in the parameters, just run it on a set of data, and you get it all. So I'm kind of expecting a bunch of products to keep popping up, which are kind of predictive analysis of many different use cases, just simply running a single query and putting it in a visual interface. But this is definitely something really interesting, and at least I'm not huge in data science and data analysis, but like this other stuff I have seen seems way more complex. And as you said, like writing your own custom codes to kind of do all this stuff will take a lot of time, and then adjusting for different things as time goes will probably be super time consuming. So yeah, so much data to study. We touched on a lot of different things. We took a little bit more time than we initially planned, but I think it was worth it. I want to thank you two again for taking the time. Ask everybody who are watching this maybe sometime later, make sure you follow, subscribe, like CODEstantine to stay up to date to the latest tech events and knowledge. We'll be sharing a lot of interesting topics in the future as well. Next week, we have Michael Dowden, the CEO of Andromeda.js. He'll be talking of how to play with Fire, basically building a web application with Firebase. So it will be an interesting topic as well. So those of you who think might find it useful, make sure to go and sign up for that one as well. Thank you all for attending or viewing this meetup. Stephanie, Palong, thanks a lot.